You know, in C++, there's this one concept that really separates the good code from the truly great code. It's called inheritance, and mastering it, well, that's the key to writing clean, reusable, and seriously powerful applications. Today, we're going to break down exactly how it works, piece by piece.
So here's how we're going to tackle this. We'll start with the absolute basics, the what and the why. Then we'll explore the different ways you can actually structure inheritance. From there, we'll dive into the rules of the road, how to control access before we unlock its real superpower, polymorphism. And we'll wrap up with some pro-level stuff.
All right, let's dive right in. To really get what inheritance is all about, we got to zoom out for a second and ask a really basic question that every single programmer faces sooner or later.
I mean, seriously, think about it. Imagine building a house where for every new room, you had to pour a brand new foundation. It would be a complete nightmare of inefficiency, right? Well, in programming, the elegant answer to this problem is a core principle called inheritance.
It's honestly best to think of it just like a blueprint. You can take a general blueprint for a vehicle, something that has wheels and an engine, and then you can use that to create a more specific blueprint for a car, which gets all the vehicle stuff for free and then adds its own details like doors and a trunk.
So the huge takeaway here is that inheritance isn't just about saving a bit of typing. It's about creating a logical structure in your code. It formally establishes that a car is a kind of vehicle, and that is a relationship is the foundation for writing incredibly flexible code, which is something you'll see in action when we get to the magic of polymorphism.
Okay, so let's see how this whole thing builds out. C++ is pretty cool because it doesn't just give you one rigid way to build these family trees. It offers a few different structures for these relationships, and each one is suited for a different kind of job.
First up, we've got single inheritance. This is the simplest, most common form you are ever going to see. It's just a clean, direct line of descent. Think of a car class inheriting from a single vehicle class. Straightforward.
Then things get a little spicier with multiple inheritance. Here, a class can actually pull in features from 2 or even more base classes. The classic example is an amphibious vehicle class that inherits from both a car and a boat. It's incredibly powerful for sure, but as we'll find out, it can bring some unique headaches. Now, hierarchical inheritance is like a family tree that splits. You have one base class, let's say vehicle again, and it acts as the foundation for a whole bunch of specialized classes, like car, truck, and motorcycle, all branching off from that single point. And finally, there's multi-level inheritance. This one creates a direct chain of specialization. So you might start with a general vehicle, then derive a more specific car from that, and then, from car, derive an even more specialized sports car. Each step down the line just adds another layer of detail. Okay, so we've got the different family structures down. Now let's talk about the family rules. How do we control what the new derived classes can actually see and do with all the stuff they're inheriting?
C++ gives us 3 modes to choose from: public, protected, and private. The one you pick acts like a filter. It changes the visibility of all the inherited members for the outside world. And, this is important, it also sets the rules for any other classes that might inherit from your class later on. Public is, by far, the one you'll use most of the time.
This table lays it all out perfectly, but here's the simple rule to remember. The final access level for anything you inherit is always the most restrictive one between its original level in the base class and the inheritance mode you choose. And just look at that bottom row. A private member in the base class is always off limits. It's like a family secret that never gets passed down, period.
All right, now this next part is something that trips up a lot of developers, even experienced ones. When you create an object from one of these derived classes, there is a very strict, non-negotiable order of operations that you absolutely have to understand.
It actually makes perfect sense when you think about it. You build from the ground up and you tear down from the top down. The base class constructor always runs first to lay the foundation. Then, the derived class constructor runs to add all of its specific details. When it's time to clean up, it's the reverse. The derived class cleans its own room first, and only then is the base foundation removed.
And this brings us to what is probably one of the most critical, all-caps, important rules in C++ inheritance. If you don't make your base class destructor virtual, and you happen to delete a derived object through a base class pointer, only the base destructor will get called. The derived part is just left hanging, leading to resource and memory leaks. It is a classic, nasty C++ bug.
So far, we've talked about the structure and the rules. That's kind of the skeleton of inheritance. But now we get to the real magic, the absolute superpower that all this structure enables: polymorphism.
In plain English, polymorphism just means many forms. It lets you write a single piece of code that can work with objects of all different but related types through one common interface. You don't even need to know exactly what kind of object you have at the time you write the code.
Just look at the difference this makes in practice. On the left, our code is rigid. It only knows how to work with car objects. But look at the right. We're using a vehicle pointer. Now that pointer could be holding a car, or a truck, or a motorcycle. And when we call drive, C++ figures out at runtime which correct version of the drive function to execute. That is incredibly powerful and flexible.
So how do we flick the switch to turn this on? It all comes down to one little keyword: virtual. By marking a function as virtual in the base class, you're basically telling C++, hey, just a heads up, a derived class might provide its own version of this function, so be prepared to look it up when the program is actually running.
Okay, let's start to land the plane here. We're going to tackle a classic challenge that comes up because of multiple inheritance, and then we'll wrap up with some expert advice for using all of this stuff effectively and safely. Remember multiple inheritance? Well, this is its most famous problem. It's called the diamond problem. If you have two parent classes, B and C, and they both inherit from the same grandparent, A, then the final child class, D, ends up with two separate copies of everything from A. This creates a massive ambiguity.
Exactly. If you try to access a member from A through an object of D, the compiler basically throws its hands up and says, I have no idea which path to take, the one through B or the one through C. It's a real problem. But thankfully, C++ gives us a very elegant way out.
And the solution, believe it or not, uses that same keyword we just saw, virtual. But this time it's applied to the inheritance itself. By making the inheritance from A virtual, you're telling the compiler, hey, merge these paths. I only want one single shared copy of the grandparent class in the end. And just like that, the ambiguity is gone.
So this all brings us to some really important, hard-won advice. Use inheritance thoughtfully. It's perfect for true is-a relationships. But for has-a relationships, like a car has an engine, you're almost always better off using composition. That just means putting an engine object inside your car class. It's cleaner. And always design your base classes for extension by using virtual. And don't be afraid to use the final keyword when you want to say, this is it, no more changes.
So now you have the blueprint. From the basic family structures to the absolute superpower of polymorphism, you've got the tools. The difference between good C++ code and great C++ code really does come down to mastering these ideas. So the only real question left is, what are you going to build with them?